On number 7, they ask which of the following properties of a light wave is bottled in particle-like lumps: wavelength, frequency, speed, or energy. Well, it turns out that it's only the last one, only energy. So if I were to do my best to draw the light wave, we still think it's a continuous wave like this. It has wavelength, it has frequency, it has speed, and all of those things just keep coming. You can have any amount of wavelength you want. You can have any amount of frequency that you want. You can have any, you're going to have a speed in a vacuum of 3 × 10⁸ meters per second, but you could have a slower speed in another material. But it's the energy that you can't have any amount that you want. You can only have energy in little bundles. Now, in some courses, we cover a thing where we say that the amount of energy of one of those photons, that is one of those little lumps, is a constant, Planck's constant, times the frequency. All it is to say that you can only have certain values for that energy, and that's the part that's quantized. Number 8 says, imagine that you're moving in the same direction as a beam of light. As you increase your speed, how does your measurement of the speed of the light beam change? Well, it turns out that it doesn't. If you were moving here and the beam of light was moving here too, well, you're going to say that you think that its velocity is the speed of light, c. Even if I took your speed away and I just told you to stand there while the light went past you, you would still say that was the same thing. Now that's funny about light, because if it was something other than light, say if here you were and there was a baseball that went past you, then right now you'd say the velocity of the baseball over the earth was, well, whatever it was. But if you started moving in that same direction, you'd think that that velocity was less than it was before. That rule goes for baseballs and other things, but doesn't seem to apply to light. No matter how you're moving, you're going to observe the speed of light, the same speed, regardless of what you're doing. Number 9 says, how is the speed of a distant galaxy related to its distance from Earth? Well, we have reason to believe that the universe is expanding. And so that means here's Earth and here's a distant galaxy. And because the universe is expanding, it's moving away from us. Edwin Hubble actually noticed that the farther the thing is away from us, the faster it seems to move away from us. And so if I say I had galaxy, 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 galaxy like this one that was close would be moving away from us, but it would be moving with a certain speed. The one that is a little farther away, a little bit faster. The one that's even farther away, even faster. And the other one, well, off the screen, faster. And so Hubble noticed that the universe is expanding, and it seems like the farther things are away from each other, the faster they're going away from each other. Number 10 talks about what is the basic defining characteristics of a photon. Well, when I draw a photon, we know that it's supposed to be a little particle of light, but it still has wavelength and so forth too. So I always like to draw just like a little wavelet kind of thing like this. And so these are my photons, and I'm not the only one that draws them like that, but there are other ways too. Sometimes people draw them as little specks or things like that. Nonetheless, there's our photon. It has 2 defining characteristics. Number 1, it has no mass. It's a massless particle. That's why it's able to travel at the speed of light. And number 2, it can only take on certain integer multiples of the Planck's constant in terms of energy. And so the energy that it has is equal to Planck's constant times the frequency. Now in the honors class, we won't get into the Planck's constant so much, but that's something, if you are interested, you could easily look up. So all that is to say, the energy of each one of those photons is a certain discrete or quantized amount. Number 43 asks, is a photon more like a particle or a wave? That's a good question, right? And as I talked about in the lesson video on this, it's kind of both. If you force me to pick, I might say it's a little bit more like a particle, but it's still totally like a wave. It has wavelength, it has frequency, it has wave speed, it has period, it can interfere. I could take two of them and I can interfere at a spot. It does everything that a wave does. The reason that I might lean a little bit more towards a particle is because of the energy being quantized idea. And so it has a certain amount of energy. It's not like you can just let the wave deliver as much energy as you want. So because of the quantized amounts of energy, I might lean a little bit more towards a particle, but you have to admit that certain times it acts like a particle and certain times it acts like a wave.